Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome to day 60. Day 60 of NL Math Man's Math Helps Dreams. Here at the same math time and the same math channel. That's right. Uh, yeah, today we are indeed, as it says below, we are traveling through time at the speed of 1 second per second, because I am not currently moving at relativistic speeds. Therefore, the rate at which I'm traveling through time is simply, you know, Newtonian, purely Newtonian. We're not getting into relativity quite yet, although we are going to talk about some Newtonian mechanics today because we're going to be talking about some physics. Right? This will be the second time I think on stream that I've done primarily physics. I'll probably have a bit more to do tomorrow as well because I'm sort of working through what one student has there. Um, for today, though, before we get started, I did want to mention a little bit another story about traveling. Actually, you know, I said I've been rummaging a little bit to try to find things to talk about for my last week because, of course, right, we're going up to Friday and then we'll be done with NL Math Man, at least for season one. Maybe I'll reprise season two in the fall, but we'll see. We'll see how that goes down. Uh, yeah, no one's 100% sure what education is going to look like in September quite yet, right? Um, yeah, so what I've got behind me here is another shot from Scotland, from my second Scotland trip. This is when I was in staying in Drumnadrocht, which is just south of Inverness, along the shores of Loch Ness. And each day when I was there, I did do a fair bit of hiking because that's what I was there to do. Now, granted, some of the hiking that I did was just, as this day that I'm going to talk about, was kind of just striking out across a road and just walking as far as I found the road to go. And the thing about being in Scotland is, after a while, you get used to the weather patterns that are there, right? And maybe it's just what it's like everywhere in the world, but it's not what it's like in Newfoundland. In that, in Scotland, pretty much every day, like clockwork, it would rain. It would rain like literally every day, but it would rain for like an hour, maybe less, like 45 minutes or so, where like the clouds would open up and it would pour rain, and then it would stop. It would stop and it would be done, right? And that would happen like literally by this point we see in this picture behind me, this was near the end of my trip. So I had been there hiking for like 6 days at this point, right? And every single day this happened. And usually after the rain, it would clear up and it would get gorgeous and bright, and you'd see rainbows and double rainbows, and you would wonder like, whoa, what does it mean, right? All this sort of stuff. So eventually, you sort of right, you use some inductive reasoning, I guess. Hey, look at that. We're not talking about that topic today, but hey, we use some inductive reasoning and we draw a pattern, and we use that pattern to sort of predict what's going to happen, right? So on this day 6 of my Drumnadrocht hiking, I struck out south along the loch, and I just sort of followed the roads and then sort of took some other paths off to the side. And it started to rain. It started to rain and pelt, and the heavens cracked open and poured, just like every day that I was there up to that point. So I figured, hey, I got my coat with me. I was prepared for this. I have my backpack with me because I always take my pack with some supplies when I go hiking now, as opposed to that Greek hike, which was just idiocy. But I talked about that the other day. Um, yeah, so I pulled, my backpack has got um, this rain shield built into the bottom of it. So you take that out, pull it over the backpack, right, and you put up your hood and all that. And I just figured, well, I'll just tank it. I'll just put up with it for the 45 minutes or so, um, and then I'll get a bit wet, but whatever. Like my feet will be okay because my boots are fairly waterproof, and then I'll just keep on going, right? But on this day six of my glorious Drumnadrocht hiking trip, it didn't stop. I gotta tell you, Twitch chat, it didn't stop. It didn't stop. It kept raining. It kept raining, and it poured and it poured and it poured. And I was still going forward because I was counting on it stopping, like my inductive reasoning had said happened every other day, right? So I got to this field behind me. It's not a super special field or nothing, right? This is not like the most scenic shot of Scotland in the whole world, but this is the part that I was passing. So to me it makes sense, right? Because this is the actual day when this story was happening, and you can't really see it in this picture very much, but it's steady raining here, right? The camera, I guess, wasn't good at catching the raindrops in flight or whatever. But the sheep are doing okay. But I guess they're animals, right? They're made to be outside. It was really starting to pelt down. I was at a loss for what to do because I kept heading forward because I'm an idiot, right? We've established that before. And I guess I should have turned around as soon as I was out there for an hour or so, and it kept raining. But I figured, it's got to stop eventually, right? And I didn't want to lose a day. This was my last day, my last full day there. The next day I was leaving to come back, right? Because this was day 6. I had a week, right? And then I was leaving. So I kept going forward, and it kept raining. It kept pouring down, and eventually, I sort of wound through the woods, and I came to this. I came to this little spot. I saw. Well, okay. I should back up a bit. I saw a sign. I saw a sign on the road that said cafe, cafe this way, like 2 kilometers. And I was like, what do you mean? Just a cafe, just out here off this trail, like just out in the woods, off of a, you know, what sort of a cafe is this? So then I went and I kept going, and I saw this spot, right? This spot here behind me. And it doesn't really do it justice, but there's all kinds of knickknacks. There's like garden gnomes and stuff. There's loads of different stuff here. It's very dense and very colorful. Loads of different things around. There's, like, you see the old station wagon over there on the side above topics, right? A super dense, super clustered sort of spot. And it was really, really homey looking and really interesting, right? And then I go inside past this, like, really, you can see the building. The building is actually what's here behind my head. It's like covered in, I guess, stucco on the side or whatever, right? But inside it was this really super old construction, really gorgeous, gorgeous little hut, basically, right? Oh, it's brickwork, yeah, brickwork, I guess, with stucco on the outside. And you can see my backpack over there behind the topics words, right? But the backpack is at this point, you can see the sort of the rain shield down around it, but it's soaked. It's absolutely drenched, as am I at this point, right? But I'm just lucky. I'm just lucky to duck in out of the rain for a bit. And I get in here, and it's a place called Loch Ness Clayworks, apparently. Loch Ness Clayworks. And, there's these two people in there who are like, boy, they could have been pulled straight out of Tolkien. Like the guy was for the world, like, what was it? Oh, I can't remember his name now. In The Hobbit, that like dude who turns into a bear or whatever, and like has all these, has the dwarves over, and it's like the last. It was not the last homie house because that's Rivendell, but this kind of felt like Finding Rivendell. But the guy inside was like, was it? I keep thinking of something that begins with a B, but anyway, who's huge. This is a giant man. He is a solid 6'4", at least 6'5", and like just big. Like, what this dude was off 400 pounds was not much. Like, this is a massive guy. And they're in there, and they're renovating this place a bit, right? You can see over here to the right that there's a bit of work being done. And he's got this little small menu up, this little small menu up above my head here. So I order a cup of tea and a piece of blueberry cake, right? Just to have a bit of vittles, I guess. And then I started going around, and I see that there's also, I don't have any pictures of everything inside here because I got a little bit self conscious about taking pictures. I'll tell you why, Twitch chat. Because in the next room there was a kiln, an actual kiln, like it was right out in the open. This huge, massive kiln, and there was this woman there, this redhead sort of Scotch woman, I guess, Scottish woman, and she was like, this is a woman. This is like a statue, right? She is. I mean, she's as tall as I am. She's a solid 6 feet, and with this like pottery smithing like apron on, with the kiln blasting fire, and with the tongs and the gloves and all that, and firing pieces of clay and stuff. And it's like, whoa, this is amazing. Like, who are these people just out here just firing clay works? And me now looking around, picking up pieces of pottery and looking at them. I'm trying to have a bit of a conversation, just to, I don't know. I don't usually do this kind of stuff. I just figured, hey, maybe I'll be a bit personable, have a conversation with these people, act like I'm a normal human being, instead of just a shut-in who plays video games and talks to no one on the internet. So I start trying to have a conversation with this like statuesque redhead that's in there, and immediately I mess it up. I put my foot directly in my mouth. I basically say, wow, it's amazing to see a place out here like this, because I didn't think very many people would come here, right? Because it's so far off the trail. I say, like, many people come here. And she turned to me and looked at me. Like, the first thing she said to me is like, well, you came. I was like, that's an excellent point. That is an excellent point. And like, I heard her husband, the other guy in the room, he just breaks out laughing. He just laughs like a really big belly laugh, like the kind of laugh you would expect to come out of like a 400-pound, 6'5" Scotsman, right? I must have turned redder than her hair at that point. But I had to admit that was an incredibly good point, right? And it was, yeah. We ended up talking a bit after, and I bought a piece of pottery. You can see it. You can see ones like it over there on the side. I wish I had it with me. I was going to do this talk earlier, this little story, right, earlier on, because I wanted to at the show and tell. But it turns out I don't have the mug with me. It must be at my parents' place, I guess. I must have left it behind when I moved one time. But it's this tiny little mug, and for the world Twitch chat, I guarantee you, it looks exactly like the pots from Legend of Zelda. Like it's got that same sort of dark brown with like the curvy little like different color around the side and a tiny little handle. It's like a pot from Legend of Zelda, but with a handle on it. It's gorgeous. It's the best mug I own. Um, yeah, so I kind of figured I was obligated to buy that after I sort of insulted these people in their own home, and and put my foot directly on my mouth, probably saying something that they hear a lot, but has become a bit of a pet peeve for them. Turns out they sell a lot of their stuff over the internet. As you imagine, a small little pottery shop off of a random trail in Scotland would. Well, we got to talking, and the Scotsman, he told me he was going back into Drum, driving back into Drum, and he would give me a ride back. Which, I mean, bless him, right? Like it was a solid 2 hour walk to get back, and it was still by this point still pouring rain out there. So it turns out, I had an excellent piece of blueberry cake, a nice mug of tea, bought the best mug I ever owned, and managed to have a nice story about traveling out of it. Right? We talked on the way back about Scotland and Canada and compared the two and talked about how a lot of Scots people in Canada and all this kind of stuff. Right? It was turned out to be an amazing day. One of the best days of hiking that I've had. And it wasn't even to do with the hiking really. Like the hiking was some of the worst hiking that I've experienced. The absolute just complete drenching of rain that I had from this scene. But hey, you know turns out to be, I guess a very human, more interesting story of traveling than I would have just got just keeping to myself and you know never venturing out to I don't know, interact with other people perhaps. But I will adamantly refuse to learn a moral from that story because I don't intend to change my self isolating ways. Right? I was self isolating before it was cool. Right? anyway, anyway, yeah. Just wanted to take apparently 10 minutes or so to tell spin a little yarn here this afternoon. Right? I say that every day. I say afternoon every day. But anyway, I'm going to get into the math or actually physics first here today. So we're going to talk about distance time graphs. We're going to talk about a bit about average speed and a little bit about instantaneous speed. So Troy, these are some questions from your notes that I'm going to be doing here now. I haven't gotten through all the notes yet, but I will get to those for tomorrow for the rest of them. So there might be a few more topics that I'm going to bring up tomorrow. But for today now, I've got a few over here. Now, I have, again, right, I don't have a digital copy of this textbook. So, the copy over there to the side is a little bit scuffed because I scanned it in, but it looks pretty good. This is Physics 1104, and this is going to be page, I'm actually going to go in reverse order of the pages, but this is the order that the guide tells you to complete these pages. Page 400, I'm going to do questions 3 and 5 here today. But we notice that we are dealing with average speed, like it says over here. And of course, from a formula standpoint, average speed is, of course, just the change in the distance, right, over the change in the time. Right? We've seen these symbols plenty by this point. Right? So we look down here at number 3. This is the one I'm going to do first. If a cat is running at a constant speed of 10 kilometers an hour for 5 seconds, what is the average speed and what is its instantaneous speed at 4 seconds? Well, that's, Troy, as you correctly pointed out in the notes, this is a bit of a foolish question, isn't it? Right? Because it tells you the answer right there in the question. And yes, sometimes when we have questions like this, it is just as easy as what it's saying. It's a bit of a silly example to start off with, maybe, but it's a constant speed of 10 kilometers an hour. What's its average speed? Well, geez, seeing the speed is constant, the average speed is going to also be 10 kilometers an hour, right? What is this instantaneous speed at 4 seconds? Well, also 10 kilometers? This seems silly. But no, that's correct. That's absolutely correct. Right? It's just a bit of a nonsensical question. The reason I wanted to talk about this question was for 3b. The cat is walking at 2 kilometers an hour, then accelerates constantly to a final speed of 14. What is its average speed? Right? So 3b, what do we have here? Like what values are we given in the question? And for physics questions especially, I like to do what we call declare variables. But basically declare variables is just sort of writing down the parts that you know, right? And then the parts that you don't know. So then you know more clearly what it is that you're working with. So 2 kilometers an hour then accelerates constantly to a final speed of 14 kilometers an hour. So we have a change in speed, or a delta S, is going to be of 12 kilometers per hour, right? Um, what is its average speed? Excuse me. Boy. So if the change in the speed is going to be 12 kilometers an hour, well, the average speed is really just going to be, right? We're told that it accelerates constantly. So all we actually have to do here, oh, actually, we don't even really need the delta speed, do we? We don't really need the delta speed because if we were to look at this, say, on a graph, right? This question is a little bit different than the ones that we've seen so far. But imagine we had a graph, right? Like this. Where over here is the speed, and this over here is the time, right? So it accelerates from 2 kilometers an hour, accelerates constantly to a final speed of 14. So it goes from 2 all the way up to 14, say like this. Now this is really, really, really rough, right? But how are we going to find the average between the 2 and the 14? Well, we don't actually know the amount of time. We're not given the amount of time, so it really seems like we don't have enough to solve this problem. But all the average is going to be is just the value that's right in the middle of it, right? Because if the acceleration is constant, then the increase in speed is just going to be totally linear like this, right? So if we're trying to find the average between this linear quantity, all we're going to have to do is 2 plus 14 divided by 2, right? We're just finding the middle value between the two of them. This is, again, right, this is a bit of a basic sort of bare bones question because they give you so little as far as, as far as resources that you can use to solve this question goes. But all you're doing is you're just saying that that's 8 meters per second. Because if it starts walking at 2, accelerates constantly to a speed of 14, its average speed over that whole section is going to be 8 meters per second, or just right in the middle, right? Because it's moving totally constantly, right? Um, although I do think, Troy, from seeing your notes, I think you have a really good understanding of this unit because it looks to me like most of the ones that you found difficult were the ones that are genuinely like kind of just weird questions, right? It's too bad for anybody watching the stream who isn't specifically doing this course because it's going to seem like every example I'm doing from this one is just it's just bonkers and not like the normal types of questions that you would have. So instantaneous speed, so number 5 is the next one I'm going to do, as you're seeing here. Instantaneous speed is a slope of a tangent to the curve of a distance time graph. That's true. It's an important fact. Show how it will be possible to use 2 or more tangents at different points along the curve to calculate acceleration. Okay? So I'm going to show this in a few different ways, right? But actually, you know what? No, I won't. I was considering drawing it out on graph paper exactly, but seeing I'm drawing this freehand, we're just gonna rough it a bit here, right? So this is going to be distance time graph, right? So we're going to have distance here, and then time here, right? And imagine a world in which it changes something like that, right? So how to use 2 or more tangents at different points to calculate acceleration? Well, we know that the slope of a distance time graph is going to be the speed, right? Okay, so, and then, but what is the acceleration? We know that the acceleration is just delta, the change in the speed over the time, right? Not usually going to use speed, I'm going to use velocity, or v, right? So the acceleration is, of course, the change in the velocity over time. So if we get two different tangents, well, let me just draw like two rough tangents to this line here. Like say I picked a tangent down here, like so, and say I picked a tangent up here. Like so, right? Now I'm not, again, right, because this is just rough and I'm just drawing this out on paper like so, we're not going to really be, this may not be 100% accurate, right? But I'm just going to ballpark this one. Well, say the speed here, say this was 2.5 meters per second. Say that was the slope here, right? Because that's relatively steep. And say this one over here was, I don't know, 0.8 meters per second. This one over here. That's what the slope worked out to be, right? Well, now we can get the delta V, right? Because we know that our delta V here, our delta V is going to equal our 0.8 minus our 2.5. So we always do T2 minus T1. And T2 minus T1 is going to be a negative 1.7 meters per second. So we know now that the speed has decreased between this point and this point. Then what other value do we need? Well, we also need the time, right? So we need the time that's associated. So we need to go down from that point, and we need to draw a line down from this point, the points at which we took the tangents, so those two, right? And then we need to find the time for those. So let's say this was, I don't know, let's say this was 0.5 seconds, and this one up here was, say this was 3 seconds, right? Oh, it should be delta V over, I guess delta V over delta T, kind of, but like we see below, right? Time is always going to be the change in time, though, isn't it? So we know that the time, or like I said, I will write delta T here. So we know that the delta T is going to be, we always do T2 minus T1. So that's going to be geez, what am I doing? That's going to be 2.5 seconds. So then to get the acceleration, all we're going to do, right, is put our, like we had over here, delta V over delta T. We have negative 1.7 meters per second, divide by 2.5 seconds, right? And that's going to give us a value of, where's my calculator? Here it is. 1.7 divided by 2.5, negative 0.68 meters per second squared. All right, and there we go. So that is how you would, so instantaneous speed is a slope of a tangent, right? So how it will be possible to use two or more tangents at different points to calculate acceleration? Well, now we have, right? Because, of course, our tangents give us the velocity, and then with two or more, obviously, we can get a delta V. Now, that, of course, tells us the average change between these 2 points. It doesn't really tell us, as we can see, it's accelerating, decelerating, which is really not really a concept in physics, decelerating. We can say it, but I mean, it's just negative acceleration, right? We can see that the deceleration, or the negative acceleration, is much more significant here, and it is much less significant here, right? So if we found the acceleration, say, between this point and this point, it would be a much sharper value, or a much lower value, actually, because it's going to be negative. But it would be a much lower value than, say, between here and here. That's how we would go about finding that. And what error might there be in the situation? Well, there's always, if we're drawing it freehand, there's always the error of us choosing our tangents at the right point. We're drawing our tangents correctly. Tangents are very difficult to draw 100% correctly unless you're using technology, right? But also there's the fact that this is just average, right? This is just an average acceleration, right? So it doesn't count the fact that the acceleration would be, like I said, far more negative here and far less negative here, right? Yeah, so we'll call this one here P1, and this one here is going to be P2, like I was saying. Okay? So that's two significant sources of potential error in a question like this one. And I wanted to do, let's see, I wanted to do page 376, number 4. Like I said, Troy, I am not totally through your notes yet. There's a fair bit there, and I have an exceptional amount of work to get through this week because, where this is the last week, people tend to be handing in a lot of stuff all at once, try to get their courses done and out of the way. Not that I mind, but it does mean that things might take a little longer to get back than they would otherwise. So this is going to be page 376. We're going to look at number 4. So let me zoom in a little bit on our page over here. So 2 runners, Tew and Laura, compete in a marathon race. In one particular part of the race, Tew has twice the average speed of Laura. Compare their distances traveled during the same time interval. Well, yeah, I mean some of these questions, honestly, like half the time, I understand why these ones are confusing, right? Because half the time it seems like it can't be that easy, can it? Well, I mean, if Tew has twice the average speed of Laura, how far is Tew going to travel in the same? It's going to be twice the distance, right? Is that spelled? Is that a man's name? Is that a? I don't know. Right? It's not hard, right? Compare their times required to run the same distance. Well, right? Well, let's go through and actually do a good faith example of it instead of just writing down the answer that we might know intuitively. But we know, of course, that velocity is equal to distance over time, right? So if T's average speed is twice as much, but we want D to be the same, right? Then we're going to have a half down here, aren't we? Because it's going to have to multiply out to be the same number, right? So we could look at it like this way, right? So if their distance is the same, right, dt equals so d for Q equals distance for Laura, like that, because both their distances are the same. We know then that the come on now, camera, coordinate with me. So vt equals d. I'll just rearrange it like that, right? So we know that v of t times time, because their time is going to be the right, is going to have the equal velocity of Laura times time for Laura, right? That just makes sense. So we know that both those are going to be equal. But now we're told that in the question, right, that the velocity of Tu equals twice the velocity of Laura, right? We're told that. So we can go and sub that in. We can go and sub that in over here, right? So we can, in place of Vt, we can write 2 times the velocity of Laura, right? So 2 times the velocity of Laura times the velocity of Tu equals the velocity of Laura times the time of Laura, right? So this is a really long-winded way of going about this, but you're going to see what I'm saying here, right? Because now I can divide both sides by the velocity of Laura and cancel those guys out. So this can cancel with this because it's the same term in both sides. We're going to end up with twice Tu's time equals equals Laura's time, right? So if twice Tu's time equals Laura's time, what does that tell us? Well, it tells us that Tu's time, we could say, is equal to half of Laura's time, right? And that's the result that we would expect to have. I know this seems a little bit confusing maybe when you're going through it. What this means is, say, say Laura took 10 seconds. Well, we take half of that, and then that's TU's time, 5 seconds, right? If Laura took 30 seconds, TU's time is going to be 15 seconds, right? But I mean, you probably knew that just from thinking about the question. This is the kind of sort of derivation of it that we can go through to use our algebra to prove it. But we know for sure that I'm not super concerned if you go through and derive it out this way, but the reason this worked, right, is because the distance for the two of them was going to be the same, which means if the distance is the same, then the velocity times the time is going to be the same. And we were told from the start that the velocity of one is double the velocity of the other. So then we can go through and solve and just get this relation that compares the time of both together. Sort of an overworked way of doing a pretty simple question. How would their distance time graphs compare? Sketch the graphs. Okay. I'm just going to obviously sketch a very simple one here. Say this is, right, so this is going to be distance and time here. So this will be TU, and then, I'm missing a pin. I am missing a pin. That's unfortunate. Okay, well, I'll do it in black then instead of red. And then so Laura is going to look something like this. We'll just say Laura's slope will be half of TU's slope, right? Not a super complicated sort of proposition there for that one. Yeah, so even though I sort of alluded to I was going to do a fair bit on these topics, unfortunately this course is maybe a bit simplistic in the way that it looks at it, but we're almost through the physics stuff for today. I am also going to look at this question here. And Troy, again, I had where I've been going through and correcting stuff sort of fast and furious here today. I didn't have time to generate any other examples of these ones. After I link you the video and you talk to me a bit about it, or you watch it rather, or maybe if you're watching it now, you can let me know if you would like me to do some more questions like this one. This is a really good type of question, and you are likely to see it on your final again after. I am a little bit surprised that the course didn't go through and show you any of these yet, but these are totally fair game sort of questions that you will see on other activities, right? So this is question 21. And let me just draw out. I'll draw an accurate graph here for this one. So they go. I'll go 8 blocks. 1, 2, 3, 4, 5, 6, 7, 8 blocks up that way. There we go. I'll go 12 this way, just to make mine twice as big as their one. So this is going to be speed over here. Speed in meters per second. This one here is going to be time in seconds, right? So we've got 0, 5, 10, 15, and 20. 0.5, 1.0, 1.5, 2.0, 2.5, and 3.0. So I guess we're to assume that after the 3 seconds, this ball rolling down a ramp simply just clunk. It's just done. It just stops. Maybe it hits a wall or something like that. But if it did hit a wall, you would have a whole bunch more calculations to do, right? With it bouncing back from the wall, and you would have loads of other calculations that you do get into. You do get into that sort of calculations in Newtonian mechanics with like the velocity at which something would rebound when it comes back and the force at which it would hit and all that kind of stuff. So keep in mind that these sort of situations that we're looking at in Physics 1104 are quite a lot simpler than what you're going to get onto later on. Personally, I think it's a lot more intuitive when you get onto it later on because you know in reality that like if the ball was rolling down, it's not just going to simply stop. Like the motion isn't just going to disappear at any point, right? It's always going to have some sort of rebound or something like that. So sometimes looking at it in sort of a simplistic way like this is actually less intuitive to my mind. But anyway, the point is to find the right. So what is it that we were asking for? Never mind. The distance, right? Find the distance from a speed or velocity time graph. We find the area on not under the graph, area under the line. Right, and we always take the area um, down to the axis here, obviously, right? We stop at the axis. And I should say, yeah, I'll be super pedantic and I'll change this to velocity because it needs to be velocity, not distance, not speed, sorry. And why? Why is that? Well, because speed doesn't have a directional component. Speed is always positive. Velocity can change, right? So, for example, the um, if the ball rolled down and hit a wall here, if it started rolling back the opposite direction but at the same speed, its speed would still be the same, would still be 20 or whatever it is, 17, 17 and a half, I guess it is right there, meters per second. It would still be exactly the same speed if it bounced backwards. However, we wouldn't then be able to use the area under said graph to find the distance because the distance from the starting point, once it's rolling backwards, is actually removing distance, right? It's going back the way it came. Or if it went off to the side in a different direction, well, then all of a sudden you've got you're not getting your full speed component is not actually affecting the distance that it's moving. But then we're talking about multiple dimensions. You do see that as well, right? Which can be solved actually with simple trigonometry, which is again something you do get onto, and I think personally, I think it makes a lot of sense once you start seeing it. But this needs to be a velocity time graph, not a speed time graph, and I am intentionally being extremely pedantic about that because it's a fairly major point when you get on to the later physics courses that, velocity has a directional component. And the directional component is what allows us to use a graph like this to accurately determine the distance that it has moved. Speed does not have a directional component, so it becomes a little bit meaningless if you change your direction because your speed can stay the same, but your direction changes, and therefore your distance is not changing at the same rate. Anyway, all we had to do to find this one, now I think you understood this from the conversation that we had earlier, you definitely understood what we were doing here, is that we do have to find the area under this graph. But the area under this graph is actually a compound shape, in a sense, right? We're not going to use the area under a graph is also known as the integral of the graph, which is something you'll get into if you do calculus. We're not going to be discussing that here, and we don't even discuss that in this program at all. But it's a thing that I like to bring up because it shows how, to my mind, physics actually points out the usefulness of the math that you learn in your math courses quite a lot better than your math courses do a lot of the time. And physics, especially early physics, and I don't just mean early as like derogatorily, but I mean like even up through undergrad, physics is kind of just like applied math, sort of, which is again not to demean it. It's really important to know how to apply math and what it means when you're applying it. Hold on a second, I do have a should check and see what that message is. Okay. Sorry, there was I'll have to respond to that after the stream is over. That's text from my colleagues about some other stuff. It's weird, right? It's weird in this day and age that like sometimes you'll have to check your text messages, and those text messages will be like that will be the actual thing that you should be doing at that moment is checking your text messages because it's the important work stuff. Because normally, like, if a teacher checks her text messages during class, like, all class gets up and they're like, "What are you doing? You said we can't use our cell phones. Then you're on your cell phone." Bad teacher. Anyway, so we need to find the area of this triangle, right? But of course, the area of a triangle is a half base times height. So we need to get the full area under this line here. So to get the area of this triangle, well, what is the base? The base goes from here over to here. So the base is going to be 3. Area of the triangle is going to be a half times 3, and I'll put in the units, 3 seconds. Because putting in the units, to my money, actually helps out quite a lot because we'll actually start seeing why it's going to be distance once we put in that, right? And then the height of the triangle goes from 0.25 to 17.5. So it's going to be 15 meters per second is that unit, right? And yeah, maybe I'll do this in black. It seems like the green is a little bit harder to see there. What with the grid lines behind what I'm writing. Right? So we're going to have the area of the triangle is going to be a half times 3 times 15. It's going to be a half of 45, which is going to be 22.5. So that's 22.5. And you notice here this is seconds and this is meters per second. So the seconds are going to cancel out and we're going to be left with a unit of just meters. Right? And then there is also this area down below here. And in a calculus sort of setting, this would be sort of taken care of by the constant term, the plus c sort of thing, right? But anyway, that again would be that's math for a lot later. That would be if you went on to do math or physics or something like that at a university setting. Now, I'm sure some college programs get into calculus as well. It is quite useful in some real world applications for sure. So then the area of the rectangle is of course just length times width. So the area of the rectangle here is going to be, well, the length is going to be 3, and then the width, or I guess the height in this case, is going to be 2.5. So the area of the rectangle is 3 times 2.5, which is going to be 6 plus 1.5, 7.5. 7.5 meters. Right, I should have put in my units again just to do a good show, right? But anyway, it's again, right, it's 3 seconds times 2.5 meters per second, which is going to equal out to be 7.5 meters. And then of course, our area total. Usually I use subscript T to mean total, but I use it to mean triangle here. 22.5 plus 7.5, which equals, of course, 30, in this case, 30.0 meters. So that is indeed the answer there. Yeah, the activity that you did earlier today sort of butchered that one. It didn't have, the multiple choice answers were not even like close to being right. But yeah, that's what the answer should be. That one is indeed 30. And you will see other questions like this, because what it really breaks down to, this is just a compound shapes problem, right? Weirdly enough, this is the kind of math that we beat to death in some of the math courses, but they never really tell you applications for it. But then you get onto a physics course, and all of a sudden it's like, hey, this is math that I did like in the equivalent of grade 9 courses, but all of a sudden I'm using it for this physics stuff, right? There's one more I'll mention on here really briefly, Troy, is just this number 24. This number 24, I know you brought this one up today because, yes, it is indeed drawn incorrectly on here. What I'm saying when I sent you that message after is that this part here, the beginning of the line, that should have been here, and for whatever reason, it's slanted down a bunch, right? But then it says, what is the instant speed at 2 seconds? Well, it should have been 5, right? Because once you see that this should be moved up about half a block, this whole thing should be moved up about half a block, which means that 2.0, instead of being here at 4, it will be here at 5. But as drawn there, of course, none of these answers work, which is why I told you to skip that question. But but as drawn, the instantaneous speed at 2 seconds is of course 4, right? But instantaneous speed from a speed time graph is, yeah, it's not exactly super difficult to find, is it? You just literally read it off the graph. Okay, but that is that's all that I have seen today for those physics ones. Like I said, I will probably have a, well, not probably, I don't know. I haven't nearly finished your notes yet. So I might have some more things to talk about tomorrow for those ones. But for today, that'll be all for the physics ones. I am going to go over now a little bit of counting problems and probability review after I wet my whistle. Some good hydration and caffeine, two of the most important food groups. Okay, so Calais, this section will be for you. I'm going to go down through a few questions on the review sheet that you submitted earlier. I just managed to get through it here today, and I will be sending you corrections and stuff shortly after the stream is done. Oh, that one's a bit small, actually. Yeah, let's go back over to here, and I'll change my background. Yeah, let's go back to the iceberg. Okay, so the first one we're going to do is number 4 over here. So Jessica is playing a game of solitaire using a well-shuffled deck of 52 cards. Lays out 5 cards face up, determine the probability they will all be spades. Okay. Also, the probability of getting a spade flush immediately in a game of 5-card draw, right? It's interesting when you start looking at probabilities of this, right? Because a game like 5-card draw, when you see it played in movies and stuff, like people are getting like full houses and like royal flushes and stuff all the time. Like the probability of those hands, especially in a game where you get one draw, is like ridiculously massively low, like foolishly low. This is 3101A Unit 3. This is going to be Unit 3 review. It's going to be question 4 over here. Okay. So, yes, well-shuffled deck of 52 playing cards, sort of like what I have over here. She lays 5 cards face up, determine the probability that will all be spades. So we know we're looking for probability, first up. If we're looking for probability, we're always looking for favorable over total, right? Well, again, right, so we're looking for 5 spades. So well, maybe not the greatest flush in the world, the 9 high flush, but it's still a flush, and flushes are pretty strong, right? But so if we have this hand, or if we have this hand, or if we have this hand, is that the same? Yeah, of course it is. Of course, that's the same hand. All those are the same. Therefore, order doesn't matter, right? So we are going to use NCR and not NPR, right? So we're favorable in this case is going to be, well, there's 52 cards in a deck of playing cards, right? Oh, sorry, this is going to be total. My mistake. The total is going to be 52, right? And we're choosing 5 of them. That's just how many 5-card hands there are, because as we just saw, with the order doesn't matter of the cards, right? So that's 52C5, and I'll go ahead and I'll just calculate them over here right now. So we know that that's 52 factorial over 5 factorial times 47 factorial, which is going to be 52 times 51 times 50 times 49 times 48 over 5 times 4 times 3 times 2. Right? So now we can just go ahead and do that in our calculator. 52 times 51 times 50 times 49 times 48. And I know that 5 factorial is 120. So that then is the number, right? So it's going to be, that's a relatively common number that we see, this 2.6 million, because that is, like, we talk about decks of cards a lot in this unit, right? So the total number of 5-card hands in a deck of cards is it's a relatively common statistic to see. So you might even remember that number at this point. And what's our favorable here? Well, how many spades are there? Because we don't want 5 cards of any suit, right? So we're not just looking for the flush possibility. We're looking for specifically a spade flush possibility exactly. So 5 spades. So there's 13 spades, and we're picking 5 of those guys, right? So that's going to be 13 factorial over 5 factorial, 8 factorial, which is going to be 13 times 12 times 11 times 10 times 9, divided by 5 times 4 times 3 times 2, right? 13 times 12 times 11 times 10 times 9. Divide by 120. Going to give us 1287. So then our probability is going to be 1287 divided by 2,598,960. 2,598,960. Boy. That is times 10 to the negative 4. So if we see that come up, you haven't, I don't think you've done any sections like this explicitly so far. But that e negative 4, you might see that kind of thing come up in your calculator. You do need to know how to resolve that sort of thing, right? So that's going to be times 10 to the negative 4 is what that means. And what that means is you take your decimal to get from this, which is scientific notation, back to the actual number. You're going to write out your number 495 like that. You're going to take the decimal, and then you're going to move 4. Here we're going to move 4 places to the left. Where you're going to move the decimal a number of places equal to this number here, with negative meaning left and positive meaning right. So we're going to take this and go 1, 2, 3, 4. And that's where our decimal goes. And now all these extra spots, we fill those in with zeros, and we normally put a leading 0 on as well. Right? So that's the decimal value. But as a percent then, right, we just remove 2 of the zeros basically. So it's going to be 0.0495%. So very, very, very small amount to get a spade flush on the first hand dealt out, basically, right? Yep. Give me one quick second here. Yes, okay. So that is how we go about doing that question number 4. So let's carry on here. There's a few off of this sheet that I want to go over today. Question 5. A child randomly arranges 12 different Dr. Seuss books on her bookshelf. Hey, I mentioned Dr. Seuss, I think, yesterday, right? Cat in the Hat, Green Eggs and Ham, and Horton Hears a Who. Those are good books. Part of the 12 books, what is the probability that these 3 books will be placed together? Okay. All right, so what is the situation that we have? Like I say lots of times, right? When in doubt, draw it out. So let's draw out the situation that we have. We have 12 books. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 books in total, and these are all unique books. None of these are, because it says 12 different Dr. Seuss books, so we don't have any of the dividing because none of these are, well, we will have some dividing, but for a different reason. But none of these books are identical. So what's the total? Right, the total different ways to represent all the orders of all these 12 books. Well, that's just going to be 12 factorial, right? Because there's 12 items, and we know that if we want to put 12 items in different orders, there's 12 factorial different ways to do it. But then what's the favorable? Let's do favorable in a different color. Well, what's the situation for the favorable ones? Right? The favorable is a situation where there's a group of 3. Remember, because we want those specific 3 books, Cat in the Hat, Green Eggs and Ham, and Horton Hears a Who. We want the 3 of them to be together. So that's our favorable situation, right? So this sort of one is combining parts from 2 different units that you've done already, right? So we've now got a situation where there's a group of 3, and then there's a larger group, right? So the group of 3 then is going to be. Hold on just a second there. It is odd that I have misplaced my red pen. But I appear to have indeed misplaced my red pen quite severely. Oh, there it is. How did it get over there? Weird. Okay. So the favorable then, well, there's 2 situations going on here, right? So there's this group of 3 here. So, of course, we know a group of 3 is going to have an order of 3 factorial. But then what else is happening in the favorable situation? Well, there's also this overall group here. And just like we've seen before, right? This overall group is 1, 2, 3, 4, 5, 6, 7, 8, 9 items that move independently, and one group of 3 that also moves. But that group of 3 moves as independently as any of the other items. So that's 3 factorial, 10 factorial, right? Because of the green section and the red section. So then our probability, we know the probability is favorable over total, right? Which in this case is going to be 3 factorial, 10 factorial over 12 factorial, which is going to equal out to be 3 times 2 over 12 times 11, which is going to be 1 over 66. Right, now 1 over 66. This is fine. It's fine to leave it as 1 over 66, but you can call that, it's going to be 1.5%, right? Because we see it here, and if we move the decimal 2 places over, 1.5%. Okay? So you don't necessarily need to convert into a percent there if you don't want to, but you're totally free to go ahead and do that. Do question 6 here as well. We're going to do 6, 9, 10, and 13, and then we'll be done. We'll be done with parts on this unit. So Liam and me can't. That's a quote that I'm not going to finish. He draws 2 marbles, one after the other, without replacing the first marble. The probability that both marbles are red. Okay, well he has 9 red marbles and 5 blue marbles. That's an important detail. So, was the probability that both marbles are red? This is not a super hard question, is it? Well, because he has, what's the probability of the first one being red? Well, there's 9 red that we're looking for out of a group of 14, right? And then he has 5 blue. So, sorry, the next one is also going to be red. So there's going to be 8 red left over out of 13. So it's going to be 72 over, I don't know 14 times 13 off the top of my head. 182, right? It's going to be 39.6%. So it's about a 39.6% chance. Part B, he draws 3 marbles, one after the other, with replacement. What is the probability that all 3 marbles are blue? Well, with replacement, these are now not dependent events, right? Now here I could have written it out as, probability of A and then probability of B given A, which is what's going on here, right? But yeah, we've covered that already. In this one, these 3 are all totally independent, so it's not going to be all that important here to write it out in such a way, right? So we know that there's 5 blue marbles out of 14, and that's going to go back in. He's going to pick again, so it's going to be another 5 over 14. Or he's going to pick again, so it's another 5 over 14, which is the same as 5 over 14 to the power of 3. We could write that as, because it's just 3 of those multiplied together. And then, if I was to do that, 5 over 14 to the power of 3, it's going to be about 4.6%. Right? Because we see that if I was to take this decimal move at 2, I would get 4.55555, and that would round to 4.6. Okay, part C was the reason I wanted to show this one, more so than the others. He draws 2 marbles, one after the other, without replacing the first marble, with the probability of drawing 1 red marble and 1 blue marble. Now, it doesn't say 1 red marble, then 1 blue marble. It says 1 red marble and 1 blue marble. So this can either be, we can either do R, B, or B, R, right? Either of those situations are going to work. So, RB then, red then blue. Well, we already know what red then blue is. Red then blue is the same as up here, right? We already did that one. So that was red then red. Never mind. Don't mind me. But anyway, it's going to be 9 out of 14 times 5 out of 13. And then an OR, right? What is the symbol that we use for OR? Well, OR is add, right? Remember, these 2 things have to both happen. So this is an AND, which means these had to be multiplied. This one here is an OR because we only need one or the other to happen, either RB or BR. So this one we add. I don't want to beat that to death, but that is an issue for a one that's coming up shortly. So this is going to be now 5 out of 14 times 9 out of 13. And of course, those 2 things are going to work out to be the same. because it's just multiplication is commutative. So either 9 times 5 or 5 times 9 is going to be the same thing in the end, right? So we're going to have 45 over 182 plus 45 over 182, right? Because it's going to be over 182, the same as up here. It's going to be 90 over 182, or 45 over 91. But either way, 90 over 182. It's going to be almost 50%. So it's going to be 49.5. 49.5%. Okay, so let's carry on here. Let's do, what question was that? That was 6, yes. So we're going to do number 9, 9, 10, and 13 we're going to do. 8 friends, including Nicole and Miriam, are lining up to have their picture taken. The probability that Nicole and Miriam will be next to each other. This is number 9. So we have 8 friends. 1, 2, 3, 4, 5, 6, 7, 8. We can represent it like this. This is the most straightforward way of representing it. So does the order matter here? Well, of course it does, right? Because what we're discussing is the chance that they're going to be in order or not. So we know we're looking for total and favorable because we're looking for probability. So our total is, of course, going to be 8 factorial because there's 8 friends and they're all in different orders, right? It's the probability that Nicole and Miriam will be next to each other. Well, what do we have for that sort of situation, for a favorable? Well, 2 of them now are going to be together. So now we have a section to apply here. So there's going to be 2 orders there within the green section. And then we have a red section here, which is the orders of all the rest of them, which again, right, we have 6 individuals and 1 group, which is going to make 7. So then the probability is going to be 2 factorial, 7 factorial over 8 factorial, which is going to be 2 over 8, which is going to be 1 over 4. Okay? 1 over 4. I do believe, Kelly, I believe you did that part correctly. We're going to keep on going down here now through the rest of these. What's the odds against Nicole and Miriam being next to each other? Now remember, odds are odd. Odds in favor is favorable, a ratio of favorable to unfavorable. Odds against is a ratio of unfavorable to favorable. Right? It seems simple when you write it out like that, but it can be a little confusing when you actually get down to it. So the odds against here, well, if it's 1 out of 4 probability, we know this is favorable and this is total, right? So if favorable is 1 and total is 4, what's the unfavorable got to be? Well, it's 4 minus 1 or 3. So it's going to be 3 to 1. So there's 3 to 1 odds against Nicole and Miriam sitting next to each other. What's the probability that they won't be next to each other? Now this is the one that I really wanted to do this question for, Kelly, because this is sort of a trick. This is sort of a little gotcha question, right? That they kind of try to spring on you because teachers are sneaky and we pull sneakies on you. But the thing is, Nicole and Miriam either have to sit together or not together, right? These are binary events, right? In the sense that they either happen or not happen. But 2 of these are complementary events, right? Because they have to either be together or not together, right? So all we're going to do here is do the total probability is 1, right? Because that's the overall probability of these events occurring. Right, 1 minus 1 over 4. That's exactly right. Yeah, that's right, TM Wolf. Good job. So that is going to be 1 minus 1 over 4. So it's just going to equal 3 over 4, or we can call that 75% if we want to call it the percentage, right? We could have called that 25%. Right? But that question there is perhaps a lot simpler than it might appear at the start. But it is worth knowing that sometimes we'll pull a sneaky on you and just stick in some question that's actually way easier than the rest of the stuff that you've been doing thus far that activity, right? Okay, so we're going to do questions 10 and 13 here now. Let's go question 10. School focus group consisting of 7 students is chosen from level 2 and level 3. There are 8 level 2s and 10 level 3s. Probability of the focus group having at least 5 level 2s. Okay. So this one's going to be a little bit more significant. There's going to be a fair bit more to do here. But we know that probability, right? Probability is always favorable over total. So we know that we're going to need to get our total as well. So let's just knock that out of the way first. So what's the total going to be here? Well, it doesn't matter the order that they're chosen, right? Because it's not like they're a sports team, not like they're playing baseball or something, and it matters who's first base and who's second, right? The order that these people are chosen doesn't matter because it's just a focus group. So we know that we're going to be using NCR because the order doesn't matter, not NPR. So it's a group of 7 students, and we're choosing from 18 students. So it's just going to be 18C7 is going to be our total, right? And I'll keep doing these out by hand because we've been doing them out by hand all along. So it's going to be 18 factorial over 7 factorial, 11 factorial, which is going to be 18 times 17 times 16, 15, 12 over 7 times 6 times 5 times 4 times 3 times 2, and so on like that. All right, but rather than crunch all the numbers in my calculator, I'm just going to do 18C7, like so. We end up with 31,824 different possible groups in total, right? Because this is just ignoring what sort of class they're from. This is just taking all 18 students and saying we need to pick 7 of them somehow. So that's the different ways of doing that. So now what's our favorable going to be? Well, we're looking for at least 5 level 2s. So at least 5 means it's going to be 5, it's going to be 6, or it's going to be 7 level 2s. So we've got 3 situations that we have to combine here, right? So how many level 2s are there in total? Well, there's 8 level 2s, so we're either going to need 8C5. Now, if we have 5 level 2s, we still need to get to 7 students in total. So we also then, we need to do 10C2, because we had to get up to 7 in total. Now, Calais, one of the main reasons I wanted to point this one out is because here now, again, right, it's really relevant what the different symbols mean. So this, we use and when both things had to happen, and when it's and, we multiply, right? When something or something else can happen, then we add, right? Because we can either have 5, or we can have 6, or we can have 7. So this is now going to be 8C6 times 10C1, which I barely even need to figure out, right? And then it's going to be, because that's just going to be 10, and this is now going to be 8C7 times 10C0, right? So it is a bit of number crunching for this one, but this bracket over here is pretty easy, and this one here is easier as well. So instead of going through and taking all the time to do it out, I'm just going to use the calculator for these ones because I've shown so many NCR on here done by hand, and from your activities, you seem to be definitely understanding how to do those ones. So I'm not going to belabor that a ton. So we have 56 times 45 plus then 8C6. Oh, we're not really seeing that. Not really seeing the TI-84 very well where I was holding it there, are we? 8C6 is 28 times 10C1. Well, we know anything C1 is itself. So it's 28 times 10. Plus, remember, anything 8C7, well, that's the same as 8C1, right? Because if we're choosing 7 people, it's kind of like we're choosing one person not to pick. Because it's C. If it was P, it'd be way different. But because it's that, 8C7 is just going to be 8. And of course, right, let me just show you in here. 8C7 is going to be 8. And then, of course, anything anything C0, well, I put 8 again, but anything C0 is 1, right? Because like I explained before, if you're choosing 0 of a group, how many different ways are there to choose 0 people? Well, just one. You just don't pick anybody. That's it, right? So now we just have to go ahead and add these guys together. So we have 56 times 45. Right? So that's going to be 27, 28, 2800, 2808. That'll be, right? Plus 280 plus 8. Yep, 2808. So that is our total number of ways to get the situation that we are looking for. So remember, our probability, like we wrote down up top here, is going to be favorable over total. So here our probability is going to be 2808 divided by 31824. There we go. And I'll just cut to the chase and turn that into a percent. So it's going to be about 8.8%. Because remember, we multiply by 100 to get from decimals to percent. So there we go. Question 10. And Calais, I had one more to do for your course here. So that's going to be question 13. Okay. A and B are non-mutually exclusive events. Now, what does that mean? Well, that means that both A and B can happen. All right, so let me just write out the stuff on the top here. 3101A, Unit 3 review. Question 13. A and B are not mutually exclusive. The probability of A or B is 85%. Probability of A is 45. Probability of A is 45. And probability of A and B is 30. What's the probability of B not occurring? So we're looking for B not. Okay, so they're getting a little bit twisty here, but it's really not all that bad. We just have to take it one step at a time and write down what we know. Now, the most important thing to do to start off with these guys is we know that we have to write down our formula, right? Our formula is probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Remember, that's because if we just added these together, we'd actually be counting the overlap twice. So we need to subtract the overlap. And now once we have this formula behind us, we're totally able to go ahead and to solve this question for all the other pieces, right? Because we're told the probability of A or B is 85%. We're told the probability of A is 45%. And then A and B is 30. I could have rearranged the formula first, but I don't think it's that important to do that, right? Now I'll just simplify the left-hand side the right-hand side, sorry, as much as I can. 15% plus PB. Subtract 15 from both sides. So we know that the probability of B is 70%. And that's not what we were asked for, is it? What we were asked for is the probability of B not. But we know that probability of something happening plus the probability of that thing not happening, that's how we represent it, remember, with the prime in the corner. Those two add together is always going to be 1 or 100%. Right? So in this case, we know that probability of B not is going to be 100% minus probability of B, excuse me. So in this case, %30%, right? And that's all there is to that one. It's not a super difficult question. The main thing you have to remember here is to apply this formula, right? But as soon as you apply this formula, I think it all falls together fairly neatly here for those ones. Okay, so Calais, that is all that I was going to get to today. Let me leave you with a nicer picture. Let's see, that was another picture of the Loch Ness clay works. Let me get that's a good one. Yeah, I like that one with my backpack in there. That's a good one. Let's get the topics out of there too, so you can see it a little bit better. That's a cool picture. Yeah. All right. Thanks for being here with me today. I'm going to go now and get some of my paperwork and correcting and stuff done here in our last week of distance teaching for the summer. Thanks for being here with me today. I hope it's been entertaining, compelling, and helpful and sleep inducing. I don't really hope it's sleep inducing, but it probably was. So, I'll just sort of live up to that. All right. Stay safe out there, and I hope to see you all again tomorrow. Thanks.